Hello, welcome to the class on E540 Advanced Electromagnetic Theory and Antennas. I am Professor Rakesh Singh Chatterjee. So now in this class we'll discuss about the method of images. So what is this method of images? So in order to understand the method of images, we'll consider the image current problem, classic image current problem. What is this classic image current problem? This classic image current problem actually consider a horizontal current element J above an infinite conducting plane at a distance d. So we are considering a horizontal current element J above an infinite conducting plane at a distance d. And we want to find the fields in the upper half plane above the infinite conducting plane. I want to find the fields because of this horizontal current element. So this is a very complicated structure system which we are considering, but by applying the method of images we can greatly simplify this problem. So how does it work? The first thing is that we want to remove the conducting surface. Because of the conducting surface, calculation of the field was very difficult. So now I want to remove this conducting surface. So when I remove this conducting surface, the boundary condition which was there on the conducting surface, what is the boundary condition? The tangential component of the electric field was 0. But now if I remove the conducting surface, that boundary condition will not be satisfied with the original horizontal current element which was located at distance d above the infinite conducting plane. So now in order to satisfy this boundary condition at that location of the conducting surface which we have removed, we need to introduce another horizontal image current of same magnitude and direction in the opposite direction, and the distance from the boundary surface should be d in the lower half plane. So with this image current element, horizontal image current element of same amplitude in the opposite direction, at the same distance from the boundary surface, will be able to get the boundary condition of the original problem. What was the boundary condition of the original problem? It was that the tensile component of the electric field was 0 at the interface in the perfectly conducting infinite plane. That condition can be satisfied. So now this boundary condition is satisfied, then from the uniqueness theorem the solution is okay. Solution is correct and unique. So now because the current J and its image J dash gives the 0 tensile electric field on the boundary surface, so we have this equivalent problem. So this is basically how method of image works. We'll discuss this pictorially in the next slide. So let us look at the original problem. Original problem is I have an infinite conducting surface, and at the distance d above the infinite conducting surface I have a electric current density J, which is shown by the red color arrow here. Direction of the current is shown by the red colored arrow here. So this is the problem. See, we have two plane, upper half plane and lower half plane. I am interested in finding the fields in the upper half plane. Inside the infinite conducting plane, I am not interested in finding the fields. I know that it's already 0, but above the infinite conducting plane, I want to find the fields everywhere in the upper half plane because of this horizontal electric current density d above the infinite conducting plane. So this is a very complicated structure because of the inclusion of this infinite conducting plane, but I will apply method of image and simplify this problem. I will find an equivalent problem. So this is what we have. The first thing I will be doing is I will remove this conducting plane, infinite conducting plane. It was difficult to find the fields because of this infinite conducting plane. I will just remove it. And we know that from the original problem I have horizontal current J, which is directed along the red arrow shown here in the figure. So now in that case, this horizontal current density J alone won't be able to satisfy the boundary condition we have for the perfect electric conductor or infinite conducting plane. What was the boundary condition? The tensile component of the electric field was 0. But that won't be satisfied. We have already removed the perfect electric conductor. So in order to satisfy that boundary condition, I need to introduce a image current density at a distance d in the lower half plane, and whose direction is in the opposite direction, and it will have the same amplitude. So these two electric current elements will give you the boundary condition at the perfect electric conductor or perfect conducting surface, infinite conducting surface of the original problem, which is shown by dashed line here. In the dashed line, it will give you the boundary condition of the original problem. Tensile component of the electric field is 0. So this is an equivalent problem. So I would be able to solve the fields everywhere in the upper half plane by using this image principle. So let's see what we are doing is correct or not. I mean, we need to justify it using the uniqueness theorem. So in order to do that, what was the original boundary condition? Tangential component of the electric field was 0. What is the boundary condition at the dashed line in the equivalent problem? It was also giving you the same original boundary condition of 0 tangential electric field. So same boundary condition is satisfied for the original problem and the equivalent problem using the method of images. So we don't need to worry about the solution is whether unique or not. Uniqueness theorem tells us that it will give the unique solution, the only solution we have. So now this uniqueness theorem makes sure that in the upper half plane, the field we are calculating from the original problem and from the equivalent problem using the method of images are same. And this was a particular case when I have a horizontal electric current density above a perfect electric conductor or infinite conducting plane. We would be able to extend it for different cases when we have a perfect electric conductor or perfect magnetic conductor, or we can have a vertical electric current density or horizontal or vertical magnetic current density. So those things we'll discuss in the next 2 slides. So we want to summarize the image principle. We can derive it, but derivation is a lengthy process, but we can always summarize and remember what is the image principle for electric wall and magnetic wall. Electric wall is when we have the electric conductivity equal to infinity, and magnetic wall is when we have magnetic conductivity equal to infinity. We will try to summarize for the image principle. So let's look at this diagram here. This diagram here, let's look at it. What do we have? In the original problem, we have an infinite conducting plane. We have an infinite conducting plane, and for the infinite conductor, we have sigma equal to infinity. This is an electrical wall. So in that case, I will consider that 4 different kind of sources. The first source is, all the sources are at the distance d above the electric wall. First source is a horizontal electric current density shown by red arrow here. Second is a vertical electric current density, and third one is the horizontal magnetic current density, which is shown by blue arrow here, and we have vertical magnetic current density, which is shown by blue color arrow here. So J is the electric current density, M is the magnetic current density. So we want to apply the image principle and find an equivalent problem for this, so that I can find the fields in the upper half plane easily. So first thing is, we consider 2 reasons, reason 1 and reason 2. I am not interested in finding field inside the conductor. So in reason 1, I am not interested in finding the fields. So I am finding the fields in reason 2. Reason 2 is the upper half plane. So the first thing we'll be doing is we remove the perfect electric conductor, because of the perfect electric conductor it was difficult to find the fields. I will just remove it. When I remove the perfect electric conductor, I need to make sure that the original boundary condition we have on the perfect electric conductor should be satisfied at the dashed line we have here. So in order to do that, when I have a horizontal current density J, I should actually find a proper horizontal electric current density image, and for this particular case the image should be also located at the same distance from the interface in the lower half plane, and it should be of same amplitude and opposite direction as that of J. For the vertical current density J, the image should be in the same direction at the same location D below the interface, and direction would be same and amplitude would be same. For the magnetic current density horizontal case, the image would be located at the same distance D from the interface in the region 1, and the direction would be in the same direction and amplitude will be also same. The image for the vertical magnetic current density M would be in opposite direction, and it should be also located at the same distance from the interface in the region 1, and amplitude would be same as that of M. So this is the classic image current problem for electric wall. We can also consider the classic image problem for magnetic wall. So there is a typo here, this should be magnetic wall. So for the magnetic wall, obviously sigma M tends to infinity, perfect magnetic conductor is there, and so we are considering an infinite magnetic wall, and we are considering the image problem for 4 cases. One for horizontal at a distance D from the interface, and we are considering the horizontal electric current density, vertical electric current density, and horizontal magnetic current density, which is shown by blue arrow here, and vertical magnetic current density. We are considering these 4 cases. So you have a magnetic wall and you have 4 different cases of electric current density and magnetic current density, horizontal and vertical, both for electric current density and magnetic current density. So we want to find an equivalent problem. So this magnetic wall was creating problem for us. It was very difficult to find the fields in the upper half plane. So I will apply image principle, and the first thing I will be doing is I will be removing this magnetic wall. So I just remove it. So it is shown by gas line here. This was the place where your magnetic wall was there. So now I am interested in finding the fields in region 2. I am not interested in finding fields in region 1. Obviously fields are all 0 here. So now for that, since I have removed the magnetic wall, whatever boundary condition was there at the gas line should still be satisfied by this equivalent problem. So we need to find images for all the 4 cases: horizontal electric current density, vertical electric current density, horizontal magnetic current density, and vertical magnetic current density. So for the horizontal electric current density, which is shown by red color J here, what should be the image? Image should be located at the same distance in the region 1, distance D from the region 1, and the direction of the electric current density, horizontal electric current density, is same as that of the original problem. Amplitude will also be the same. And for the vertical electric current density, direction is in the opposite direction. For the vertical case, direction is in the opposite direction, and it would be of same amplitude, and the distance from the interface, which is shown by gas line, would be same at the distance D in region 1. The image for the magnetic current density, horizontal magnetic current density, would be in the opposite direction. For the vertical magnetic current density, image would be at the same distance from the interface in region 1, and it will be in the same direction, and amplitude will also be same. So we have discussed the classic image current problem, equivalent problem for using method of image for electric wall and magnetic wall for horizontal and vertical electric and magnetic current density. Let us summarize it. So how is the principle of constructing image? How do we find the image? So the main principle behind finding the image is, after putting the image, we should actually get the boundary condition of the original problem. So the image and original source together should produce the same field which was existing in the original problem at the boundary, at the interface. Then you can obviously delete the boundary. no need to worry about the boundary, you can just remove it. And in the process, since we have properly satisfied the boundary condition at the interface, the field you calculate in the upper half plane will be same as that of the original problem. It will not affect the fields in the region of interest. So now what we have considered was horizontal and vertical electric and magnetic current density. But in real life, the current density, electric and magnetic current density, can be in any arbitrary direction. It cannot. It can be horizontal, also vertical, also it can be in any arbitrary direction. So the question is, this image principle we have just discussed, is it applicable for any current density in any arbitrary direction? Because we have discussed only horizontal and vertical case. Yeah, it's you can always apply this image principle even for any arbitrary current distribution. How do you apply it? First thing is very simple. No? See, let's say you have any current distribution in any arbitrary direction. You can always decompose into horizontal and vertical components. Then apply the image principle on the horizontal and the vertical components. So whatever image principle we have discussed for electric wall and magnetic wall, even though we have discussed only for horizontal and vertical case, it is applicable for any arbitrary current in any arbitrary direction. That's all. Thank you.